Yeah, okay, thank you. So thanks for having me. My name is Antonio, and then I'll talk a little bit about the thermodynamic integration of for basically for commercial aircraft. So just to brief introduction of myself. So basically, I would say that my title is that I am a thermodynamic integration specialist, and then I'm a mechanical engineer, and I have a master's in computational heat transfer and a doctoral degree in computational fluid dynamics. So this is basically my academic background, and then I worked most of my career at Embraer in Brazil, and as a what we call a propulsion systems aerothermal engineer. Okay, and then I spent during my time at Embraer, I spent a little time in a laboratory in France doing some research. And after some years, I joined the Mitsubishi aircraft, and I am there until now. Okay, and in Mitsubishi, I am a thermal engineer. So that's my background. And now, if we go to the agenda, we can see that the idea today is that we talk about basically try to discuss what is this thermodynamic integration, okay, that we are talking about. And then after that, we will talk about the operational envelope of the aircraft, the thermal operational envelope. We'll talk about aircraft zones and some thermal requirements that we have. Right, then I'll give one example of a thermal management system, okay, just for us to have an idea of this system, and then I'll talk about thermal analysis for this example that I'm doing, and then we'll talk about some tests, and in the end talk about some challenges some technological challenges that we have now. Okay, so basically the idea is, so what is this thermodynamic integration? So thermodynamic integration is something, let's say, we are working in everything that is related to temperature in the aircraft. So basically that's for everywhere. So in all the ambients, all the systems, all the structures, all the zones of the aircraft, we are basically responsible for those thermal characteristics. So we normally use some type of analysis or some type of tests. So in your case, if you ever felt like too hot or too cold when you were traveling in an airplane, probably this is a problem of thermodynamic integration for sure. Okay, so we talk about this image later, but this is the type of analysis that we do. We try to see, for example, if a passenger is feeling too hot in their heads and too cold in their foot. So this is one issue of a thermal comfort that we deal with. Okay, so basically this is the scope that we will do. And so then when we talk about this thermodynamic integration, there is one thing that is very important that we have to understand is about this plot. It's looks a bit complicated here. I try to explain a little bit. So this is, every aircraft has to define what we call a temperature and altitude operational envelope. So basically that means it's like this. It's a plot where we have in the x-axis we have temperatures, which is basically air temperatures, outside air temperatures, ambient temperatures, and in the y-axis we have altitude. Okay, so normally what is happening is that the aircraft has to define a region, okay, and which I show in blue here, and basically if the aircraft is flying inside this region, it's okay. And if the aircraft flies outside this region, it's not okay. And of course, for the aircraft operator, the ideal scenario is that this region is as large as possible. Okay, they want to have, because that means they have flexibility. They can operate the aircraft even if it's a very cold or if it's very hot. They can operate the aircraft. However, sometimes it's not possible to have it a very large envelope because of the thermal requirements that we have for the passengers, for the equipment, for the structures, for everything in the aircraft. Okay, so that's idea. That's one of the challenges of the thermodynamic integration, is try to guarantee that the aircraft can operate in a reasonably large envelope. And when we talk about this type of envelope, there is one concept that is very important for you to understand that I will explore a little bit now, is the idea about this line here that we call ISA. So ISA means is an acronym for the International Standard Atmosphere, and this is basically a model of the atmosphere that was developed based on a lot of experimental data. And the idea of this model is to define a reference for the whole aviation community. So the ICAO, that we mentioned a lot in the previous talks. So they define this, they use this model as a reference for the atmosphere. And what this model says is like that. In a standard day, what we call a standard day, at sea level, so at 0 feet, the temperature is 15 degrees Celsius. And when we started going up in altitude, the temperature will drop linearly until it reaches minus 56.5 at 36,000 feet. Okay, so this is the ISA line. And in this model, beyond this altitude, the temperature is constant at minus 56.5. Okay, so this is a very important line, and many times we define the envelope, the operational envelope of the aircraft in terms of this line, and I'll show you right now. So just have this concept in your mind, and now we can go back to the envelope that I showed before, and you can see, for example, in this envelope, this aircraft has what we call a hot limit here, and this hot limit is ISA plus 40 degrees C. So what does it mean? It basically means that, remember, ISA is sea level 15 degrees. So this aircraft, it's ISA plus 40, so it's able to operate at sea level up to 55 degrees Celsius. Okay, so it's very good because it's a very hot temperature. So basically it means that this aircraft will have a lot of flexibility in its operation. Okay, and actually this is one of the most critical regions for the thermodynamic integration, is the ground hot operation. This is very critical. So there is a lot of work to guarantee that this temperature is as high as possible. Another one that is very critical is this one here, is number 2. So this is the ground operation, but in the cold scenario. So in this case, for example, this temperature, this aircraft has a limit of minus 54 degrees Celsius, which is also very good, which is also covers a lot of winter operations. So you see, this is an aircraft that can operate both in very hot days and also in very cold days. Again, this is critical for the thermodynamic team to guarantee that the aircraft can operate in this region. The other one that is also very critical is this one here, number 3, is the very cold but in flight. Now, in this case, this aircraft can operate up to minus 80 degrees Celsius, which is also very good. It gives flexibility, for example, to fly in polar routes. So this is very good for the aircraft operator. Okay. So yeah, this limit here, just to comment here, there is this ISA plus 35. This is normally not so critical because this is hot in flight. But even if it's relatively hot in flight, because of the temperature drop with altitude, the temperature, the absolute value of temperature itself is not so high. Okay, so this is an aircraft envelope. Maybe just one comment, maybe you can think why in the cold side, why you can operate at minus 54 on ground, and why in flight you can go up to minus 80. And the reason is because of the aerodynamic heating. So because in flight, normally you are flying at high speed at those altitudes, especially in commercial airplane, okay, in a large transport airplane. So, and basically, if you consider that, what we have to consider is the total air temperature. So, which means the temperature that is affected by Mach number. So, if we do this calculation that you can do maybe later, this type of calculation here, you can check that if you consider a Mach number of 0.8, which is like typical of cruise conditions for very large aircraft, or for these altitudes, basically at minus 80 degrees and Mach 0.8, the total temperature is minus 55, which is equivalent to this level here. So it's like this point and this point, they will be in the similar thermodynamic condition because of the total temperature, or because of the aerodynamic heating at this region. Okay, so this is just to comment that. And so let's move on. So, okay, so first we talk about these, we talk about the envelopes. Now we can talk about the zones of the aircraft. And then when you talk about zones in terms of temperatures, there is a very clear distinction between two types of zones. We have what we call the pressurized areas, which are those in yellow here in this example. And those are the areas where they are the most critical areas in terms of temperature, of course, because we have passengers, we have the crew, we have cargo, and also we have a lot of electronic equipment that are, let's say, critical for the safety of the aircraft. So in this region, basically is the region where we will use environmental control system. Okay, that I think you talk about that in the previous, I think on Monday when you had the classes with my other colleagues. I think you talk about this environmental control system. So those are the areas where the temperature will be controlled. Okay, because, and it will be controlled because it needs to be controlled because of the criticality of the passengers, of the crew, and of the equipment. Okay, that are in those zones. But also, of course, we also have many unpressurized areas in the aircraft. Are those marked in this pink or red here, and those zones, they don't have a specific dedicated temperature control. But of course, we can also we cannot let the temperature in those zones simply go anywhere. Okay, they have to be. We have to guarantee that they are within acceptable limits as well. Okay, so both all those zones, both the pressurized and the unpressurized areas, the thermodynamic engineer has to guarantee that both on ground and in flight, in the hot day or in a cold day, that the temperature is within adequate limits. So now, talking about that, I just put here some examples of when we talk about the requirements. What are those requirements that we have? So I brought here some examples that we have for pressurized areas, okay, which are the most critical that I mentioned. Then we can basically define three groups of requirements related to temperature. Okay, so we have requirements for the passengers, the crew, and the cargo. We have requirements for the equipment, and we have a fire requirement. So when you look at, let's say, passengers, so it's we have some minimal ventilation requirements, which are, let's say, safety requirements for the passengers, and also maximum concentration of contaminants. So those are things that are related to safety. But also we have many requirements related to comfort of the passenger. So requirements that are, let's say, the operator of the aircraft wants to have a comfortable environment for their passenger. Okay, so those are some requirements that we have. In terms of the equipment qualification, it's the same. We need to guarantee that the equipment, they are in an environment that is adequate for them. So the temperature limits must be adequate. And I will just briefly mention about fire requirements. In terms of temperature, what we want to guarantee in terms of when we have a fire is that the effect of the fire will not, let's say, damage essential structures around the aircraft. So we need to guarantee that the temperatures on those structures will not be affected by the fire. But I think we'll talk today. I will talk mostly about those type of let's say the thermal comfort requirements and the passenger requirements. Okay? So now we said that we have this operational envelope, we have these zones, the pressurized and then the unpressurized zones, and we have some requirements. And now looking specifically in the pressurized zones now, what we can do to guarantee that those requirements are adequate, that we are complying with those requirements. So what we do is, for example, in the cabin, there is a cabin ventilation system. So this is a system that maybe you are familiar with it, but I'll just give a quick explanation. Normally what we do, we take air from the engine compressors, and this air will circulate through, will pass through an air conditioning machine that is not shown here in this scheme. And from the air conditioning machine, so the air here is in high pressure and high temperature, and then when it passes through the air conditioning machine, it will expand. So it will reduce its pressure and reduce the temperature as well. After that, it will be transported through many ducts to the upper region of the aircraft, and then it will enter the cabin. It will circulate around the cabin, and after that, it will move downwards, okay, to the underfloor region of the aircraft. It will circulate through the electronic equipment and also through the cargo compartment, and finally, it will be discharged to the outside of the aircraft. So this is a very, let's say, very important system for the thermodynamics team. So because we have to guarantee that the airflow and the air pressure and the temperatures, they are in adequate levels in all operating conditions. Okay. So yeah, just to maybe give you now a little bit of more details on how this system operates. So I give you here, you can see, I just give you here some, I'm using this aircraft as an example and showing a little bit more details. So we can see here the engines, and you can see here the ducts. Through those ducts, the high pressure and high temperature air will be taken from the compressor, and it will go to the air conditioning machine. Okay. After that, so here is a zoom view of the air conditioner. So in this air conditioner, what we have, that is the high pressure and high temperature flow will enter this machine. It's basically an air cycle machine in most of commercial aircraft. So this high temperature, high pressure air will expand, and then it will leave this machine as a cold and a low pressure flow. Okay, that will go to the cabin now. So then we can see there are many ducts around the cabin, and you can see the air will circulate through those ducts, and then it will be moved upwards to be inflow into the cabin through the upper side, and then it will go, after that it will go to the underfloor region and circulate for this cargo compartment, for example. It's similar in the cockpit. Now you see we have many distribution ducts in the cockpit, and this duct air will be inflow in this area, and after that it will go to the underfloor region, and for example it will cool the four electronic equipment bay, which normally is in this region, but in the underfloor. And again, similar to the rear portion of the aircraft, you see many ducts, okay, and the air will go from the top to the bottom of the aircraft, to circulate here. It will pass through the cargo compartment, it will pass through the electronics compartment, and then it will be discharged to the outside of the aircraft. So this is how the ventilation system works. And what the ventilation system now has to do it has basically to guarantee that with the thermal loads that we have inside the cabin, we have to, the system has to guarantee that with those thermal loads, we have some sufficient airflow and sufficient, let's say, in the right temperature, especially, for example, in a hot day. So we want to have sufficiently cold air to guarantee that we can manage those thermal loads. Okay, so this is, for example, typical values of thermal loads that we have for crew members, for passengers, for electronic equipment, for the electronic equipment bay and the after electronic equipment bay. Basically, what we want to do is guarantee that we can manage those loads. We can manage those thermal loads by using the right amount of airflow and at the right temperature. And sometimes, of course, those thermal loads will change a lot with the specific flight condition. And of course, when it's very cold, those loads actually they will help. But when it's very hot, they will not help, and they will heat the cabin. So we have to manage that. And of course, for example, especially when we are on ground operation, we have a lot of solar radiation that we also have to consider. So basically, the analysis, this consideration of exactly what is the adequate level of airflow and what is the adequate level of temperature to be used will depend on, of course, on the flight condition that we are considering. I just put here some typical parameters that we have. So normally we have, like, when the bleed air is captured from the engines, it will leave the engines at around 200 degrees Celsius at a pressure of around 50 psi. Then it will move through the air conditioning machine, and then at the outlet it will be around 0 degrees and with a relatively lower pressure. And then it will circulate through the cabin. Okay. However, there is some recirculation. There is not only this 0 degrees, but there is also some recirculation of air in the cabin. So basically what will happen is that the air that will enter the cabin is around 20 degrees. Okay. And then after that, the air will circulate through the bottom region of the aircraft, and it will be in the electronics bay around 30 degrees, and then it will go out of the aircraft. Of course, this is, let's say, only typical flight conditions. Those temperatures will change if we are on ground or hot or cold operation. And but I think maybe the important message here that you understand that all these a system like that, it's not free. It's not free of cost. Okay, it's not free of impact to the aircraft. So this is something that we need to understand, that a system like that will cause a lot of impacts to the aircraft. So we can imagine, for example, one of the basic impacts that we are taking air from the engines. So we are taking high pressure air from the engines to use to ventilate the cabin. So this has a lot of impact on the engine's operation. So this has an impact on fuel consumption of the aircraft. If you look at the whole system, you can imagine that the whole system has a lot of thermal insulation, has a lot of ducts. We have this air conditioning machine. There are some heat exchangers. There are many valves. So the system is very. I did not show all the details, but the system is very complex. Has a lot of things, which of course cause an impact in weight of the aircraft as well. If you think also, this system will sometimes require that we have some that we capture external air, like we have some air inlets and air outlets, for example, for air conditioning or for the heat exchanging. So those inlets and outlets will cause drag also to the aircraft. And this is a system also that needs to be controlled. So there is a lot of there is a software for those systems. There are many valves. There are some fans sometimes. So it also adds complexity to the design. So basically, the idea is to say that a system like that it causes a lot of impact to the aircraft, and it has to be optimized. So this is the message. So it's mandatory we cannot simply do whatever we want with a system like that, because otherwise the level of impact can be so high that it will be unacceptable to the aircraft, to the operator, to the customer of the aircraft. Okay? So, and then this is the idea of using models and using simulation, okay, to treat this type of system. So this is why when we are talking about thermal system, thermodynamics, we have to use a lot of modeling, a lot of simulation, because we don't want to make decisions and then after when the aircraft is flying, we realize that our decision was not good. Maybe our decision was imagine if you have an aircraft that the thermal comfort is not good, or if the fuel consumption is not good because of a bad decision. So we don't want that. Okay, so that's the idea of that. When we talk about thermodynamics, we have to, as much as possible, not only thermodynamics nowadays, everywhere in the aircraft, but specifically in thermal aspects, we want to use a lot of modeling, a lot of simulation to anticipate problems and make right decisions. Okay, so that's why we started to talk a little bit now about modeling. And so normally I will talk about two types of models that we use when you talk about thermodynamics. So there is something that we call the network models. So network models are basically, let's say, they are, if you think of a hand calculation, normally is like a network model. Okay, if you do a hand calculation by, if you look at let's say if you are in a room and you consider the main heat loads in that room and the sun and the electric lights and so on, and some ventilation, you can do some hand calculation to see what is the average temperature of that room, and this is a network model. So a network model it can be as simple as that, as let's say one room, or we can do something a little bit more complicated, which is divide the aircraft divide, let's say, the cabin or in nodes, okay, and then the idea is that we select in the most important locations, we place some nodes, and then we use those thermodynamic equations, let's say related to pressure drop of the air, and also the heat transfer equations, to monitor, to calculate how the pressure and how the temperature and how the airflow will change from one node to the other. Okay, so this type of models, they are, let's say, they are not so complicated in terms of physics. Okay, they are basically things that we learn how to do this in the university. But the point is that those models, they are quite useful. They are quite useful, even if they are relatively simple in terms of physics. They are quite useful because we can use many nodes in many locations, and then we can do some parametric studies. For example, we can check the diameter of the duct. We can check the effect of, for example, of we can see if the balance of airflow is uniform in the forward portion, in the aft portion of the aircraft, for example, if we are having uniform airflows. So also we can couple this type of model with the control system we can have another model of the control system that can be coupled also with this type of model. So this is just to let you know that this type of model is very useful. And I just show here one example for you to have more a feeling. So this is, I took this from a paper. I put the reference name here on the bottom. So this is a model using a software called FlowMaster, which is one famous software that is used for this type of application. So in this model, they will, as you can see, they will set many nodes that we are called here are those let's say red squares here. So those are the nodes where we want to know what is the air pressure, what is the air temperature, what is how much airflow is passing through that division. So those nodes, they can represent the different branches, for example, of the ducts distribution system. So we can do this in the cockpit, in the forward cabin, the aft cabin. Okay, so you can imagine that this type of model can become very, very large. And as I said, the idea is to have an overall view of how is the air distribution in the different zones with this type of model. Okay. However, what happens is that this type of model, they are very good, as I said, but they are not very detailed. They are not very detailed. We just put really average values, average, let's say, pressure drops, for example, average quantities. So sometimes when we want to have more detail, and sometimes we need more detail, then we have to use what we call computational fluid dynamics model, or CFD models. Maybe CFD, I mentioned about something about CFD here. CFD basically means the type of model that you do when you want to have more details about the airflow. Okay, you want to, basically, you can say you use CFD when you want to take the real geometry into account. You really want to evaluate, consider the exactly geometry of the aircraft, because you want to be more precise in your analysis. Of course, that will depend when you are going to use CFD or not. That will depend on your application. Okay, so that's what I said. That's what I said, that the thermodynamic engineer has to balance when it will be needed to do that or not. And so one example, I just go quickly here, that when we want to use CFD is to evaluate thermal comfort. So when we are evaluating thermal comfort of the passengers, we really want to know details. We want to know how is the temperature very close to the passengers, how is the air velocity close to the passengers. And in that case, we are using a very detailed geometry. So you can have an image here of the cabin with the passengers, with the details of the seats and the windows. And in that case, we are not using just simple nodes, but we have to build what we call a finite volume mesh. So you can see an example here of this mesh. And this mesh can have many million elements, okay? Because we want to really have details. Okay, so this is just to give you an idea. And the good thing, so this type of modeling is much more complicated, but the good thing is that it gives you more information. It gives you much more detail. So you can have, as I shown before, you can have details about the temperature distribution very close to the passengers. You can have overall airflow distribution in the cabin. And also you can, for example, you can look at the air velocity very near the passengers as well, which are all parameters that are very important to do an assessment of thermal comfort. Okay, so we talk about network models and CFD models just for you to have an idea of the type of application, when we use each one of those. Of course, we cannot do only models. We also have to validate those models. So that's why we have to do many tests. Okay, but before that, I was almost forgetting about that, because maybe there is one question that you can have about these ventilation models. It's just, I will not talk about that much now. I think we don't have time. But one question that you may have is that if we can use this type of modeling to predict the spread of COVID, if a passenger sneezes on the aircraft, if a passenger will cough inside the aircraft, what will happen? So, and the answer is yes. So last year there was a lot of studies using CFD to try to evaluate the effect of that and try to show actually that aircraft, they are relatively actually safer than other environments. And actually, I think last week there was a nice study that was published in the New York Times. Okay, so there is a link here. You can just search for that in the web, and it shows a very nice CFD simulation of basically of sneeze those pitch particles are particles someone sneezes in the airplane and shows what happens when someone sneezes in the cabin. Okay. So just moving on now very quickly is just to talk about tests. Okay, so we cannot only do models and analysis. In the end, we have to do, you have to participate in many types of tests. And so tests on the aircraft level, tests on the component level, sometimes tests on laboratories. And one of the most famous tests that we do is a test in this, what we call the Eglin Air Force Base laboratory. They have a climatic laboratory. It's a laboratory in Florida. And in this laboratory, basically, you can put, it's a huge laboratory. You can put the whole aircraft inside it. And then in the laboratory, you can control all the thermal characteristics. So you can, for example, do, so in this case, we are showing this is a very hot test. So you can, for example, do in this case, it was a 50 degrees Celsius test. So you can place the aircraft inside the laboratory, and then you can operate the aircraft, operate all the systems, you can operate the engines, and then the engineers can do a lot of measurements and see if the temperature levels are adequate or not, if something has to be improved, validate the models that were used before. Okay. So this is an example of a high temperature test. We can do the same in low temperatures now. So this is a minus 40 degrees Celsius test, for example. It's a very cold test. It's the same. We can do a lot of evaluations and test a lot of things in this type of climatic chamber. So they are very important. And now, just talking very briefly now about what are the challenges that for the thermodynamics engineers now. So one of them is, we just mentioned that when we talk about safety, is lithium batteries thermal management. So it's interesting that we see there was a very famous fire in a battery in the 787 that was in 2013. Okay, and you see, and last year there was this beryllium prototype also had a fire in the battery in 2020. So you can see that this is still a problem. This is still a big problem, and nowadays we are having all those new aircraft, those new eVTOLs, and many aircraft they want to use more and more lithium batteries, and the thermal management of those batteries is really a challenge. That so there's a lot of people now doing their research and doing analysis to improve that. Okay, so this is one important item. And another important item is about these new supersonic business jets. So maybe you heard this is just one example. We have these Aerion supersonic jet. So this type of supersonic flight for the thermodynamics people, it's very important because of the total temperature that we talked some slides ago. So you see, these aircraft, they want to fly at 57,000 feet and at Mach 1.4. Okay, so if you remember what we did before, at 57,000 feet, if you look at the standard temperature, the standard atmosphere, the external temperature is minus 56.5, so no problem, it's very cold. And if you are flying in a typical commercial airplane, for example, at Mach number 0.8, then the total temperature will be minus 28, which is also not a problem. It's very cold, so it's not a problem. However, if you are starting flying at Mach 1.4, then the total temperature becomes around almost 30 degrees Celsius. Okay, so you can be at 57,000 feet at 30 degrees Celsius of air temperature. So this is very hot. Okay, this is very hot. So and this is a type of problem that this type of aircraft will face to control the cabin environment and to.
Thank you, Antonio, for very great presentation. It was very interesting. So, the student, please, questions. Okay, I have one question. I am not specialist in thermodynamics, I'm sorry, but for me it's very interesting. you talked only about temperature distribution inside airplane, yes?
Yes. Mhm.
But how it's a temperature distribution outside airplanes and according flying in supersonic or subsonic speeds, as well place of integration of engines in the airplane, in fuselage. So
Yes.
my
So
question
yeah.
is
Good.
how big impact of hot airflow is to fuselage from
Yeah.
the classical airplane, what is in this picture?
Sure. Yeah. So I think I haven't talked much about that. You are right. But basically, if you think of the, maybe I can show just one figure here. Just go back here to answer your question. So maybe here.
Mm-hmm.
So here you see, I talk about the cabin because the cabin is probably the most complicated region on the pressurized area. Okay,
Mm-hmm.
the cabin. When you talk about the unpressurized area, probably the most complicated region is the pylon. Is this region here, okay? Because this region has, as you said, it has a very hot air from the engines here, okay? And at the same, so you have a very hot stream here, and just above it you have a cold stream. Okay, so there is a lot of what we call these temperature gradients, which are not good for the structures. And also in the pylon, we have a lot of systems passing here. So we have fuel systems, we have hydraulic systems, and for example, we have this very hot air here to go to that goes to the cabin. So, and this is a very narrow, very small space. So it's really challenging to do the thermal management of this region. I would say that when you look on the outside, this is probably the most critical region.
Okay, from students, you have a question for Antonio?
I have a question. I would like to ask your personal opinion. Do you think it is safe to fly in a big passenger plane during COVID pandemic? Because in your picture we saw that air molecules are spreading in all passenger area.
Yeah. So I think if you take a look, take a look. This study is very nice. This one, if you, I think you have the slides. Okay, so if you can take a look on this. But basically, what the idea is that if you remember, when we said that the air, the cabin air, the idea is that the cabin air it will come from the top, and then it will go to the bottom of the aircraft. So basically, the idea is that the cabin air, first thing, the air in the cabin, it will circulate not throughout all the cabin. It will circulate only in some rows. Okay, so it's like so there is not a chance that a particle that is released, let's say, in the forward of the cabin will move to the aft. This will not happen because it will be removed much before that. And also, what they comment here in these, what they comment here in this study is that they have we have to remember also that there is a very good filtering in the aircraft. Okay, that I don't talk here, but there is a very good filtering that will filter most of the particles. And so I think that the conclusion from this article is that it's actually, and also it's many people in the industry saying that it's much safer to be in an airplane than to be maybe in other places where people are already, like in restaurant, or it's much safer to be in an airplane because of the level of ventilation, because of the level of filtering that we have. Okay, of course, and also what they say in this study is about the masks, because the masks will happen because there is a risk that someone is exposed for a short time, but then the mask will help to avoid that particle, that during that very short time that particle can, let's say, enter the mouth or the nose of the person. So in this article they talk about the masks.
Thank you for your informative answer.
Yeah, thank you.
Also, I have one question.
Yeah.
About simulation program.
Yeah.
Which program we use to simulate this situation?
So in this situation here is similar to, actually is a type of similar to this one here. Okay, that so normally what we do is that there is what we call CFD. So for example, in this case, there is one that is proprietary of a Siemens that is called Star CCM Plus. So this is one is nowadays very famous. So this type of program, they will do what we are seeing here. They will, of course, the engineer has to prepare a geometry, like a CAD file, and then we have to generate a mesh, which is like this. So this type of program will help in this generation of the mesh. This is not so automatic, though sometimes there is a lot of let's say manual work. So the generating mesh is something that takes a lot of time of the engineer sometimes. And then it will basically, after you have this geometry and mesh, you have to consider boundary conditions. So I think those arrows here are locations where we have to impose some airflow, some temperatures, some things like that. Or for example, in the case of the COVID simulation, you have to consider someone is releasing some particles either through coughing or through sneezing. And then what you do is that you have to solve now the fluid mechanics equation. So we call those Navier-Stokes equations. So, but we have to resolve these fluid mechanics equations. The problem of that is that you have to resolve those equations in a very large number of points. So I would say that for a simulation of this COVID, probably hundreds of millions of points you have to consider. And to do that, you need to have very powerful computers, and this type of simulation they normally takes a lot of time. Okay, so that's what we do.
Okay, thank you for your question.
Okay, we have more questions. Okay, no questions.
Okay.
Okay, so thank you for very great presentation.
Thank you.
And thank you, students, for attention. And now I would like to ask Antonio, Clarissa, Rafaela to stay here for a few minutes for summarizing. Okay?
Okay.
Okay, so